Okay, good afternoon. First, as co-organizer of this lecture, I would like to apologize for all the speakers. We are repeating some of the concepts, okay? So some of you can get bored of looking at some of the equations and some of the principles. Sorry, perhaps it was our fault that we have not done some editorial job about what was the contents, the particular contents of the different talks, okay? I will try to go fast around concepts that have already been commented here, okay? So, the talk is divided into parts. First, a bit of history about the Hall effect thruster, and then I will talk about the physics of these devices. Well, first, a picture of the device. Here you have a couple of thrusters. These are the Safran PPS 1350 that have flown in several missions. So the thruster has this annular shape. We have that the injection of the gas is at the bottom of the chamber. Also the anode is at the bottom of the chamber. So we are injecting the gas into the chamber. And then the ionization is going to take place here. And as you have already listened to, we have an external neutralizer that is one cathode. And the potential difference, the discharge voltage is going to be between the cathode and the anode. And here we are emitting the electrons that we'll see later that have a double role. The one main role is to neutralize the ion beam that is emitted by the thruster. Okay? These white walls are made of ceramic material. Normally it's boron nitride or boron nitride with something. With this ceramic material, we have a better control of the electric fields that we have inside the thruster. You can see here that we have a couple of hollow cathodes for redundancy in this case. And well, we have then all the thruster module assembly to control all the parameters and the functioning of the thruster. Okay, the whole thruster is an old invention. It was invented 50 years ago. Indeed, it was invented more or less at the same time in the United States and the Soviet Union. The first papers were US paper, one American paper, so 62. And the first paper in the Soviet Union must be around, I don't know, sure, 64 or 67, okay? So here you have the concept where you can see the annular discharge chamber in the two cases. You have here is the magnetic circuit system that we are going later to see, which is its role. You have the same here. These are coils. You have here one coil. Here they have one coil, two coils. In this case, they have three coils. The injection of the gas from the back, and here they were using the hot filaments for the neutralization of the electrons that Jaime has commented before. Okay. So, in 1971, the Soviet Union launches the first Hall thruster. It was called SPT-50. SPT is the main family of Russian thruster, or previous Soviet Union thruster. They have from the smaller one, SPT-10, to the SPT-140. That is the one that has been flown in the Airbus platform that we have seen this morning. Okay, so they have a whole range of them. That depends on the power we want to have in the spacecraft. This flown in the Meteor spacecraft. And more or less around that time, the USA abandoned the research on the Hall thruster because there are some issues about oscillation. It was more difficult to control than the ion thruster, so they thought that the ion thruster was a better thruster to develop, so they favored the research on the grid ion thruster. So in the next 2 decades, the Soviet Union launched several missions using Hall thruster for satellite station keeping, okay? And this activity was totally ignored in the rest of the world. In what is called the Western world, we didn't know anything about that, okay? It was just in 1991 with the Soviet Union fall and the subsequent diaspora of scientists that in the USA, in Europe, we knew that they have this successful engine, okay? And there was a period of 3-4 years where the Russian scientists and engineers were very keen to show us how this thruster works and how well it works. Okay? And then is when we learned the basic of this thruster. After this period of 4 years, they didn't give information anymore. Okay, they realized that they have something important and they stopped to give information on the thruster. Okay, but by then there was already intensive research programs on Hall thruster initiated in USA, Europe, and Japan. Also some joint ventures between the Russian companies. For instance, there was one between Facel and Loral, and indeed in 2004, 10 years after this joint venture, Loral launches the first GEO satellite using several SPT-100 thruster on it. Okay, these satellites are still on operation by Loral, and indeed today Loral claims that more than 50% of their satellites are equipped with Hall effect thruster. Okay, most of them for station keeping. Okay, the Smart 1 mission was already commented before. It was the first mission ever where Hall effect thruster were used for primary space propulsion. I mean, this is not for station keeping, but for change of orbit of one satellite. So there was the Earth orbit racing with Hall thruster, possibly the first time Earth orbit racing was done, okay, with this type of thruster. This took, I think, around 15 months to change from an Earth orbit to a moon orbit, and then there were moon orbit operation for around a year, 10 months, around that. Okay, all this was done with the PPS 1350, with this power, this small thrust, and it used only 82 kilograms of xenon during 10 months of firing. The mission was 2 years, and the time of firing of the thruster was about 10 months. So it was a big success. Congratulations, Jose, for that. Okay, well, we go to the issue again of the main parameters of a rocket. The Hall thruster is a rocket, so rocket propulsion, is based on action-reaction forces. We're going to see the action-reaction forces are different in a chemical thruster than in electric thruster, okay? So here the main parameters we care about is the thrust, the specific impulse, the power we have on board, and what is called the propulsive efficiency, or the thrust efficiency is also called, okay? So here the specific impulse is all the total impulse we need, that this depends on the mass of our spacecraft, and all the velocity changes or the velocity we want to provide to the spacecraft to carry out the trajectory we want it to have, okay? Sometimes we need to accelerate the spacecraft, sometimes we need to decelerate when we are entering into the orbit of a certain planet, for instance, we want to change direction. All this makes the delta V, okay? So this comes from the mission. And this gives us a total impulse, and then we arrive to the ISP. A footnote here is that ISP, when we divide the total impulse by weight, we have the ISP in seconds. When we divide the total impulse by mass, we have the specific impulse in velocity units, in meters per second, okay? When rockets were only used for launches, it made sense to use here the propellant weight because we were on the Earth. Once we are in space far away, there on Mars, Jupiter, it makes much no sense to use the weight, so it makes much more sense to use the mass, and that is why several people we prefer to work with the ISP in terms of velocity units, what you have called you before, the exot velocity. Indeed, it's an average exot velocity of the gases, okay? So this is one important parameter to characterize a thruster. The second parameter to characterize is the propulsive efficiency. That is the useful power over the total power we are putting on it, okay? And it can be expressed in this way. You have also seen in different ways. And indeed, this measures the quality of the thruster, okay? How much of the total energy is used, okay, positively for propulsion, okay? This figure varies very much. We have seen before the table that Jaime showed. There are some thrusters with 0.1, the efficiency, other with 0.8 or higher. Okay, the PPT is around here. There are certain electrons right here. The grid ion thruster is also close to here. Okay, so this is one measure of the quality. It's better to have this as high as we can, but there are other parameters we take into account. So we have already talked about the specific impulse. We talk about the quality of the thruster through this. Then there is lifetime. We have talked a lot about lifetime, how long the thruster is going to to be useful, to be operational. And another parameter that is more difficult to quantify is the simplicity of the thruster, how easy is to operate the thruster, okay? And this is very important. For instance, this morning also they have talked about this constellation, Leo constellation, and there we want more compact thruster, cheaper thruster, and then we want simple thruster, okay? So disruptive technologies try to work mainly on issues like lifetime and simplicity of the design. Okay, the action-reaction force in a chemical thruster it comes from the pressure. It's just a contact force. Okay, so we have pressure on the walls by the gas that is pushing the spacecraft on one side, and then the reaction force is the one that we have on the gas. Okay, on the hot gases. Okay, later we'll see how this works in a Hall thruster. Well, moving ahead, we have talked a lot about the propulsion dilemma, whether we want more thrust. This is thrust per unit of power. Of course, if we have more power, we are going to have more thrust. This is obvious, no? So the real two parameters is the ratio thrust to power over a specific impulse. You have seen this plot before several times, and where are chemical thruster, Hall thruster, and the gridded ion thruster, okay? Higher ISP, that means lower thrust to power, implies that we are going to use a lower propellant mass. This is an important point, but at the same time, we are going to have lower acceleration, because this is lower, okay? And we are going to have then, therefore, a longer thruster firing, okay? We need to fire the time, more time, okay? So it's very important to have low propellant mass, but because the launching costs are related to how heavy is our spacecraft, okay? But in the launching cost, or how heavy is our spacecraft, okay, there is not only to take into account the propellant mass, there are other aspects to take into account. We have the mass of the thruster system, the PPUs. We have seen before that the PPU of the T6 were weighted 47 kilograms, so this can be a heavy thruster, okay? So we need to take that into account, and we need to take also the constraint we have on the duration, of the firing duration, okay? This was very important in the case of the GEO, the GTO, on the orbit racing, how much the operators were admitting as the time for the transfer. So we have a constraint on time, and with all of that, at the end, we arrive to an optimal ISP. That sometimes is not the biggest one we can have. That is why for certain missions, the gridded ion engine is not the best thruster, okay? Because the optimal specific impulse can be closer to the Hall thruster instead to the gridded ion thruster. Okay, station keeping is what we have been doing with electric propulsion until 5 years ago. 5 years ago, with the responsibilities for electric propulsion have increased. They want to do this orbit racing, okay? Orbit racing want to be done at the maximum thrust possible with our thruster to go fast, the faster we can. But and then the station keeping, we want to use the less propellant we can, so we must work at maximum specific impulse. So it's very important to know which is the envelope of thrust versus the specific impulse of each thruster, okay? This is an example for the PPS 5000, that is supposed to fly in this Airbus platform, in the E3000E platform. And then, so we have, here we can work in all this region. Here would be the point with high thrust and a lower specific impulse, so it would be the point to work to operate at orbit racing, and this would be the point to operate at the station keeping, okay? So we need to know which are you see that we have different constraints about the stability of the discharge, thermal limits, the available power, the discharge stability, so we have to take into consideration many aspects in order to know which are the operational points for our thrust, okay? Well, then we have the all-electric spacecraft conceived by Boeing in 2012, but now all the primes are trying to have their full electric spacecraft. So here we have, these are three press releases. This is the arrival to geostationary orbit of the first all-electric spacecraft by Boeing. This is from September 10, 2015, okay? This was for 2 weeks ago, okay, when Airbus full electric spacecraft reached the geostationary orbit. It was in October 11, okay, so just today, okay. And this is also news from August 20, okay, this year, where they say that all electric satellites halfway to becoming half of all satellites, okay. So 50% of the satellites in the coming years possibly will be for geostationary satellites will be all electrical. In this case, Hall thruster seems to be better positioned nowadays, at least for this market. Okay, a comparison between the two technologies. Possibly I would have some discussion in this with Jaime. Okay, I consider that the gridded ion thruster is the upper class. Okay, is the jewel in the electric propulsion. Okay, it's our Rolls Royce. It's the best thruster we have. First, you see here that something I commented this morning, the EP family is very large, okay? All chemical rockets are the same. It's the same principle, okay? But with EP, we have a different technology. Here we have ion thruster on the top. Then we have the Hall thruster, the R-jet. I think this is a PPT. Here we have electrospace on a CubeSat, et cetera, okay? So we have many types of thrusters, some of them flying, all of them in the lab, working hard with them. And in that family, we have the gridded ion thruster. Why is the jewel? Okay, because it has the highest efficiency of all of them, practically. Perhaps there are some electrospray that can be better. It has the longest duration. We're talking about 40,000 hours. 40,000 hours is more or less 4 years of continuous operation of the thruster. Okay, the Hall thruster nowadays is between 1.5 years. 1 and 2 years of operation is the maximum we have, okay? We have also the highest specific impulse, the lowest beam diversion. I will come later a bit to that, but it's important that the beam we have has the lowest diversion we have because we have very energetic particles than when they hit the solar rays of any other equipment of the spacecraft, they can be very damaging, okay? And the Hall effect thruster, for instance, has a bigger beam diversion. And well, both of them, the gridded ion thruster and the Hall thruster have a successful story, okay? But we continue with the comparison now with the Hall thruster. It's more complex, the ion thruster, okay? It's more complex, much more complex to manage electrically. It is also heavier. It has a lower thrust density because of the child law that Javier has commented, okay? It's a bulkier thruster, so it's heavier. So what we are getting in propellant, perhaps we are losing it in the weight of the extra weight of the thruster. We must take that into consideration. All these things make it more expensive, okay? And then there's a point also that perhaps it's less flexible operationally, but I'm not sure. I should discuss this perhaps longer with Jaime, but the child law makes a constraint that I know how it works, okay? So for the moment, since that Hall thrusters are dominating the space market and even the Mars race, okay? Here we have, this is also news from October 13, ion thruster prototype breaks records in tests and could send humans to Mars. It's the first time we are reading this. In this is not an ion thruster, it's a Hall effect thruster. It's the one you are seeing here. It's a 100 kilowatt thruster. It has 3 channels. You see the size is 80 centimeters of diameter. And at 102 kilowatt, is able to give, sorry, this is not millinewton. This is 5.4 newtons. What we are having there, okay? So this is a development by NASA. Terrible thruster, no? 5.4 millinewton. So this is what we are having today, okay? In the case of low power Hall thruster, we are also considering them for near-Earth mission, Constellation, Galileo, Earth observation. We have talked about that already before. I'm not going to comment anymore. But the point is that when we go below, let's say 100 watts, 50 watts, there is a high loss of efficiency in the Hall effect thruster. We go from efficiency above a 50% to efficiency below a 20%, okay? So it's difficult to miniaturize the Hall thruster, okay? Something similar happens with the ion thruster, okay? That is why for micropropulsion, we go to different technology. Here you have some 100 watts thruster by CDTI, by the Italian company that has flown are going to fly. And this is a prototype made at MIT of 50-watt thruster. Okay, you can see how small is that thruster, and they got 20% efficiency with the thruster, which is not bad at all. Okay, let's go more now into the physics. I promise to minimize the mathematics here. Okay, so the first thing is to compare all again with the graded ion thruster. The graded ion thruster is quite Cartesian. So first we ionize, then we accelerate, and then we neutralize. And the three regions are very well separated. Okay, in a Hall thruster is not the same. Okay, we have that the production takes place more or less in this area, but then the acceleration. When we cannot finish the ionization, we are already accelerating, and for finishing the acceleration, we're already neutralizing. So the three processes take place at more or less at the same time, and we must study them in a coupled way. Okay, this is the similarities and the differences with the ion thruster. Okay. Well, what we have here is a discharge voltage that we don't have grids. So here the discharge voltage, or the potential we're going to get for acceleration of the ions, comes from this cell between the anode and the cathode. We have only one cathode, that is the neutralizer. We are using lower potentials, not 1,000 volts, typically around 300 volts. This makes the PPU simpler. Okay. Also, we have less electric points to control. The good point here is that this cathode neutralizer has two roles. Okay, it's a meter current, so we have a discharge current that, in terms of ions, in terms of electrons, go from anode to cathode. So we are spelling a current of electrons here, and we have part of them that goes to neutralize the ions that are produced here inside. They neutralize them, so we have an electron current equal to the ion current that we are emitting, and the other part goes inside. Okay, and the role of this is the role that has the second cathode in the ion, the one we have inside. So these electrons that we have here are going to ionize the gas that we are injected here. Okay? So we have electrons coming here, electrons going up there. The one that got going is here, ionize, we produce the ions, and the ions are accelerated through the electric field. Okay? This is the idea. So the born ions are accelerated from this high potential region to the low potential region. Okay? And the born electrons, the ones that are born here, continue with the ones that we have from the cathode, and they go, all of them together, to the anode, and then they are, through the electric circuit, okay, they come again into the cathode neutralizer. Okay? So the first question is how the plasma managed by itself to split the emitted electron current such that the part of the cathode current that goes downwards is equal to the ion current. Okay? This was something that it was a problem also. It's a problem for the ion thruster. At the beginning of this story, the engineers were very worried how this could work, if this could work fine or not. And this is one of the cases where the plasma is very friendly. It's a good guy. Okay? It's not the bad guy that it usually is. It's a good guy. Okay? It managed by itself to send, you go there and you go there. Okay? Why? Because if you don't neutralize the ion current, we get the thruster charge. Okay? If we emit, let's say, more ions than electrons, more ion current, so we are charging the thruster on this spacecraft negatively. This has an impact on the relative potential between the spacecraft and far away region, and this is going to decrease immediately the ion current that we are having. At the end, this has a restoring effect. Okay? So the electric fields that are created by the plasma that make that this has a restoring effect, and indeed we have a net electric current equal to 0. Okay? These are the very good news. Well, then changing to another aspect, the magnetic field. We have a magnetic field here. First, let's see how we create it, and then we'll see why we need it. Okay? We create it with coils. In this case, you have one coil here. No, sorry. Well, this is the axis of symmetry. We have a structure like this. We have one coil here. We generate a radial magnetic field. Then this is a ferromagnetic material. So all the magnetic lines go this way, We have here another coils to better control how the magnetic lines go. And then we have that the magnetic lines jump into this vacuum for them. We have no ferromagnetic material. And we have this radial magnetic field. This is the way we create the magnetic field. Why do we want a radial magnetic field? Well, just to say that some Hall thrusters use permanent magnets. I'm not going to go into this now. Well, the point is to control the motion of the electrons. If we don't have a magnetic field, and we have these 300 voltage difference between cathode and anode, then we have a free acceleration of the electrons from the cathode to the anode. The time, the residence time, or the traveling time between, the transit time between cathode and electron will be 10 to minus 2 seconds, 10 to minus 8 seconds, okay? And this time is much smaller than the ionization time, that is typically one microsecond. This means they are not going to ionize, they're just going to go traveling very fast to have any collisions with the neutral gas, okay? Because ionization is produced by the electron-neutral bombardment, in the same way that in the ion thruster. So we are not going to have gas ionization. This is not going to work. So we need to stop down the electrons. How do we do that? Well, we put a radial magnetic field. What happens when we have a radial magnetic field? The first thing is that we have the magnetic confinement. So electrons get trapped. They get trapped in the magnetic lines. If this is a magnetic line, they have a gyro motion. Indeed, I mean, this is like a kind of dance for the electron. It's a valse, I used to say. No? They are dancing, the electrons. So first, they have this gyro motion along the magnetic line. So they are trapped in one magnetic line. But if we have an axial electric field, we have what we call the azimuthal drift. So due to the combination of the electromagnetic field, we have azimuthal drift. And this means that they are not only doing the gyro motion, they have this azimuthal motion. That is why the chamber is annular, to permit them to have this super motion. Okay? So they are rotating on the magnetic line, they are gyrating here, okay? But they are not advancing. It's wonderful. Now they don't advance. We want them also to advance a bit from cathode to anode, okay? And this is done by the collision and axial drift. From time to time they are dancing and they get a collision. Well, they ionize or they not ionize in this collision. It depends on the energy they have, but then they can move a bit axially, okay? So in this case, the axial drift comes from collision. Footnote, come from collision or from instabilities that we have in the plasma. It's what is called the anomalous transport, okay? But this is a bigger problem to discuss. By the way, they have also another movement. They have a radial bouncing, okay? They also bounce between these two walls. So it's a motion composed of 4 elementary motion. What do we get for that? Basically, that the resonance time has increased by 3 orders of magnitude. It's 10 to microseconds to electron to go from the cathode to the anode. Time enough to have several ionization events, okay? In this way is how we create the plasma, okay? Well, the applied magnetic field that we have here, that we create is around of 200, 400 Gauss. This is the typical value. For comparison, the Earth magnetic field is 0.5 Gauss, and in tokamak we have 10,000 Gauss or 20,000 Gauss, 1 or 2 Teslas, if we use different units, okay? So the point here is that electrons are strongly magnetized, but ions are not magnetized, okay? They are unaffected by the magnetic field. This is done on purpose, okay? We want that the ions move axially, free, and associated by the electric field, okay? They don't want, they feel the magnetic field. How can the electrons feel the magnetic field and the ions not, okay? Well, this is just to look at the equation of motion under the magnetic field, and the effect of the magnetic field on the motion of particles is proportional to the square root of the mass of the particle. If we are using xenon, the ratio of masses between an ion of xenon and an electron is 240,000 times, okay? So we need, if we want to have the ions magnetized, we need magnetic fields that are 300 times larger to have the same effect that they have of the electrons, okay? So we need magnetic fields of the order that are used in the tokamak. Now, in the tokamak, ions are magnetized, okay? But not here. We don't want them here, okay? So we have there a nice range where we can have one of them magnetized and the other not. Let's go to thrust. How thrust is achieved in a Hall thruster? Well, the action-reaction forces that we have in the Hall thruster are of magnetic origin. That is why, for me, the Hall thruster is an electromagnetic thruster, okay? And the principle is the same one that we have when you have 2 wires that are counter-streaming, with 2 currents that are counter-streaming. What they happen? They have forces, magnetic forces that put them away one from the other. We have these repelling forces, okay, because this current creates a magnetic field, this current creates another magnetic field, so we'll have magnetic forces one to the other, okay? And this pulls them away. Well, here is the same. But the role here, the wires are going to be circular loops, okay? And on the one side, we have the loops, we have the coils. This is one of the loops. So here we have these coils, okay? These coils that are represented here. On the other side, we have seen that the electrons have this azimuthal motion that we have created, what we have called the E cross B drift, okay? And these are loops. These are current loops, okay? The ions don't have, the ions move actually, basically, okay? So we have that the electric current is the electron current, this azimuthal. So we have these loops of plasma, okay? And this, well, this is the movement, but completely we are getting these loops. So in a stationary picture where we have a certain loops here, okay? The currents in the plasma loops are counter-streaming with the current that we have in the coils. This is the diamagnetic effect that someone has commented already, okay? The plasma has typically a diamagnetic response. So the two set of currents are counter-streaming. And this is what is pushing. We have the action of the plasma coils on the thruster, on the other coils, and we then on the thruster, and this is the action force, and the other force is the reaction force, okay? So this is how thrust is produced. Well, let's talk a bit about the effect of the electric field, because I need to show you why the acceleration of the the acceleration of the ions has to do with thrust, okay? Because here I have not talked about the accelerated ions, okay? So first, the electric field fulfills Gauss' law. This is here. This is electrostatic for the electric field. So we have the diversion of the electric field is the electric charge. The electric charge comes from the contribution of the ions and from the electrons, okay? Well, what always happens is that the electric field that is controlled by the plasma, by the charges on the plasma, mainly, is to minimize the electric charge. This is what has been called before the quasi-neutrality of the plasma. So this means that the negative electric charge of the electrons is more or less equal to the positive electric charge of the ion. They are not exactly the same, because we have some electric field. What we are saying is that each of these terms is much larger than these terms. So we have still a gentle electric field, okay? But the charges are more or less compensated, okay? This is what is called quasi-neutrality. This is the same effect why the cathode is able also to split, or the electric field is able to split well the currents of the electrons going downwards and upwards or inwards. It's always this equation. So basically we have near equal electric charges of the electron and ions, and the forces on the electrons and the ions are practically the same, okay? Because we have a single electric field, so the force of the electric field on the electron current is going to be the same as the force on the ion current. This is very important to understand the next slide. So when we look at the plasma as a whole, as ions plus electrons, the total electric field, or the total effect of the electric field on the whole plasma is more or less negligible, because they compensate one to the other, okay? Is what we have here. This is quasi-neutrality. We have more or less identical, the same positive charge that would be the blue ions and green electrons. So we have this quasi-neutrality, and the electric field is pushing the ion this way, the electron this way. Forget about the magnetic field here for a moment, okay? So we have the 12 counter-streaming, but always keeping this quasi-neutrality there at every point. Why I wanted to tell that? To show you which is the role of ions here, okay? So coming back, how thrust is related to the ion momentum, the answer is that the ions are freely accelerated by the electric field. So this is second law of Newton, okay? Force, electric force, is equal to mass times acceleration of the ions. So very simple how ions are accelerated. But for electrons, we have the Lorentz force equilibrium between the electric and the magnetic force. So we have a magnetic force that is related to this axial velocity of the electrons. So the electric field makes that this is equal to this, more or less equal to this. This is how electrons behave in order that to have an electric field that makes that this Lorentz force equilibrium happens. Okay, but what we have known as the force of the electric force on ions and on electrons is the same, but of opposite signs. So if you add the two equations, what you have is that the momentum gain of the ions come from the magnetic force. Okay, so here you have the relation between them. So which is the reaction force? Well, it would be the action force. So this would be the action force. Is the magnetic force that we have on the, well, actually, it doesn't matter. Is the magnetic force we have on the electron. This magnetic force is equal to the electric force we have on the electrons. By the way, it's the electric force we have on the ions, as we have said. And the electric force we have on the ions is what gives the momentum gauge of ions. Okay? That is why we say that the thrust is the momentum gain of the ions. But we have all this relation to understand how we go from the momentum gain of the ions to the real physical force that is the thrust, okay? So it has a kind of intermediary role, the electric field. Okay, okay, fine. I have almost finished. Why the Hall thruster is less efficient and durable than the grid ion thruster? Okay, why we don't have a Rolls Royce? Okay, well, we have a penalty in efficiency and penalty in lifetime. The penalty in efficiency comes from two reasons. One is the larger plume diversions, and the second one is the larger particular energy losses. Larger plume diversions. So here, this would be the plume that we have from a certain electric thruster. So the higher it is, the less axial thrust we are having, okay? So we are losing, if we are accelerating radially, if part of the energy we are giving to the ion is radially and not axially, this is not going to be to thrust, okay? So this is why we are penalty inefficient. And why is that? First, because we have lower discharge voltages, so the energy of the ions is lower. It's easier to deflect then sideways because we are lower discharge voltage, 300 instead of 1,000 volts, okay? And then also because the plasma production is more spread. It does not happen it's what I said before. We don't have production, acceleration, and neutralization. At the same time we are accelerating, we are still producing ions, okay? So we have ions of different energy, so we have a larger dispersion on the ions. So this is a penalty. This is difficult to improve, okay? And it's a major concern, the issue of the large plume diversions on plume spacecraft interaction, that have been commented also before. But also we have larger particular energy losses to the chamber walls. Here you have an eroded chamber of one of the snake mass from the thruster, okay? We have impeachment of ions on the walls that erode the walls, okay? And this is because the energies of the electron energies are higher in this chamber than in ion thruster chamber. And then we are having the particles impact the walls with energies that lead to erosion. And then because we don't have magnetic shielding on lateral walls, this means, I'm going to comment this in the next slide, what is this issue of the magnetic shield, okay? And then we have the penalty in lifetime. This is the wall splitting, the impact of the ions on the walls. Ions are massive and can be very damaging when they impact the walls. Electrons, no, because they have almost no mass, okay? They're not dangerous to that. And so these larger particle energies and energy losses are due also to have large wall splitting. So this wall splitting we are seeing here, at the end we are modifying the chamber wall, and then this can lead to the functional failure of the thruster. So new Hall thruster design look for magnetic shield of the walls in order to try to solve partially these two problems. Okay, both the lifetime and this, and also the possibility of increased efficiency with a lower particle energy loss. So novel Hall thruster design. They use more complex topology. This is a conventional Hall thruster where we have this magnetic field that is almost radial. This means that we are able to control that the electrons don't go very fast this way. This was the main purpose of it, no? But they can go easily toward the walls. There is nothing that prevents them to go to the wall. That is why we can have a large particle. If the electrons go to the wall, the ions go also to the walls because of the quasi-neutrality and the electric force behavior, okay? The one go with the other. So this was good to control the motion of the electron toward the anode, but has the penalty that we have the strong losses in the walls. Okay. So now we go to more complex technology. In more complex technologies, we say, okay, why don't you put some magnetic confinement on the wall, so we have magnetic field that are parallel to the wall? What we are doing in the ring gas thruster, for instance. Okay. Whenever we put magnetic field lines parallel to the walls, we are preventing that the plasma go to the walls. Well, this is nice, but before we wanted this, now we want the opposite. Okay, what do? Well, we have to work hard on the magnetic topology, and we have this type of magnetic topology. So, in this way, it's difficult to the electron to go this way, also to go this way, okay, but the magnetic field is weaker here than there, so this is a preferential direction for them to go, okay. So in this way, And the experience of the experiments with the new magnetically shielded thruster, it has been positive for that. We are able to reduce very much by several orders of magnitude, two or three orders of magnitude, the erosion on the walls. Okay, and this is the most successful thruster on this aspect. Is the Aerojet X5. Okay, it's a 5 kilowatt thruster, and is the most for the moment is the reference thruster for this magnetic shielded thruster. There are other solutions to avoid this problem of the erosion of the walls, okay? But well, I don't have time to comment on them, but there are other solutions. But this one now is on the mainstream on Hall thruster, on new Hall thruster development, okay? To use magnetic shielded thruster. Okay, are Hall thruster physics well enough understood? No. Okay, there are central phenomena affecting the performances that are insufficiently understood, not enough understood, okay? We have issues with the transport of the electrons, okay? I have, going back to this, the transport electron here or there in this way is still not well understood. I have talked before about anomalous transport, okay? So we have a problem of anomalous transport for 50 years, okay? Since the 1960s, we have this problem, and we have been unable to understand it, to model it, and then to try to solve it, okay? And this has a big impact on the efficiency of the thrust, okay? This is one problem. Also, the issue of the plasma interaction with the walls is not well enough understood, okay? We have electrons that are emitted from the walls, apart from the one that go to the wall. So we don't understand very well how is the population, the details of the population of the electrons. And this also has an impact on the performance. Then we have other problems related to the oscillation of the discharge. The discharge is not fully stationary. We have certain instabilities. They are called the breathing instabilities, the ion transit instabilities, and all these instabilities make that we have oscillation of the currents and of the voltages that we have inside the plasma, and this must be solved by the electronic people. Say, okay, we have this problem, try to solve it. Try to put filter there, solve this oscillation, because we cannot control the plasma, okay? The plasma is not such a nice guy, and we have this oscillation, okay? So all these issues, mainly the issue of anomalous transport plasma wall interaction, are critical. The fact that we don't understand this quite well is that we cannot develop predictive numerical codes, okay? This would be very important, okay, to have a code that tells us how our solutions behave, our designs behave. We don't have that. These are very needed, okay, in order to reduce the cost of design, development of qualification. I mean, you want to sell a thruster and to tell to Airbus, okay, this thruster is going to have a life of 4 years of operation. We need to qualify for 4 years of operation. If we don't have full models, we need to put the thruster in chambers, a vacuum chamber like this, for 4 times 2 years, perhaps for 8 years. Because from time to time we need to open to see what happens. We have problems with the operation of the vacuum chamber. So this is a big problem now that electrical propulsion is so important and wants to go so fast. The issue of qualification is it's an important problem, and we need to have better models and then better simulation. Because we need to solve these problems that have been there for 50 years, okay? And there is a large worldwide effort, both in theory and testing, to try to get these predictive tools, okay? By the way, this is a vacuum chamber that we have in our premises in the UC3M, okay? Well, here I can show you, I hope. This is the simulation tools we are having now, but they are not fully predictive. There are some parameters that we need to include there from the empirical, from the experience we have, okay? Mainly those related to anomalous transport, okay? What you are seeing here is what are called hybrid codes. Here, these are ion particles, so we have millions of, well, yes, around 1 million particles of ion, 1 million particles of neutrals. We move them, we model all the collisional processes to create the plasma, and then from these particles we extract what are average magnitudes like this, that would be the ion density in the thruster in the chamber, okay? So this is the tools we are developing, but we need more physics, okay? And you are much welcome to help us to do that.
So after this very, very interesting talk, I hope you have a lot of questions. No? Come on, check. You don't have any question?
I have answered all of them.
This one there. I have many, so be careful.
Well, first of all, thank you for this enlightening explanation, because you have made that at least I have get some of the things that is getting here, so thank you very much. My question is actually a question to both of you and maybe the next colleague. We have seen that plasma physics are really complicated. There are a lot of things that are not well understood. But from your experience, from the DC power you have to put into your engines, which engine is the best behaved in terms of how you demand the power, how you demand the voltage, and which one is the worst, and how these things are overcome nowadays, apart from brute force from electronics or?
Well, I think that partially I have commented on that. It's going to depend very much on the type of mission and on the needs you want. Okay, as I commented before, from the point of view of using the power you are putting there, okay, the ion thruster is very good. It has an efficiency around 70%, and while Hall thrusters has only a 55%. This is how we are using the power. But at the same time, as I have commented, the PPU of ion thruster is much more complex. We are working with much higher voltages with that. So it's going to depend very much on the mission. And I don't know. I don't know if I get what the core of your question.
Yes, the answer was not how efficient, but in which way you demand the power. I mean, when you put the circuit, the electrical circuit, you put a DC source, but the current that flows through it is not entirely DC. It's a DC plus a lot of oscillations.
Yes.
This is the same for all the engines, because on the graded area in the discharge is the same. You have oscillations too.
Yes, but I think that the oscillations are quite different in one thruster or the other. I have commented here that some of them that are particularly important in Hall thruster, these what we call the breathing oscillation, are oscillation on the range of 20-30 kilohertz. Okay. And they can have a quite large amplitude with respect to the average discharge current. It can be 50% typically. And even you go to high voltages, now we want to go to high voltages in Hall thruster because we have a higher specific impulse, and then they can be even higher. You know? So this is an issue. This is a well-known issue, and usually the electronic engineers use their filters to try to minimize the impact that they have on the electronic system. And there are other ones at other levels of a higher frequency that are also important, not so important. About ion thruster, indeed, I didn't know which oscillation they have. In your talk, we have commented about oscillation, and also I think Javier Palencia. This has been enlightening for me because I didn't know anything about oscillation in ion thrusters.
There are oscillations too in ion thrusters. There are less oscillations, I would say, just because I think the main reason for that is that you don't have the E cross B drift that you have. You don't have a turbulence really in ion thrusters. You just have a DC discharge. So the oscillations you get in ion thrusters come from the fact that you're extracting ions. So you have oscillations due to the time the ions spent in the discharge. But that's it really.
Thank you very much, both of you.
Any other question? Yes?
Well, actually, we have two guys fighting each other for the market, the Hall thruster and the GIE. Which do you think will have more weight in the market? Who can move more money in the few years? I mean, actually in these really competitive markets, who enters with the money maybe can improve their designs better than the other one. Which do you think will maybe win that battle?
Well, I think that we need a referee, José Antonio, but it's better that you answer this question than any of us.
Well, you know, we have a lot of money put in this just to decide which one is the best. So if I tell you they don't need us, European Union doesn't need us, no. Okay, every thruster has a different properties. And today, what is true is the Hall effect thruster is more expanded. It's 70% of the spacecraft in the world they use Hall effect thruster, and about 30% they use ion engines. In the past was the AHEDO, but the AHEDO now is superated. So what we saw here is that for some applications, Hall effect thruster is really the best. Like at this moment, they want to go very fast from GTO to GEO, so Hall effect thruster is good because the power to thrust ratio is low. When you go to station keeping, ion engine is the best because of the specific impulse is very high, so you save. If you have interplanetary missions, ion engine is also good. So there is a lot of interaction between one and others. And when you look at the market and at the different companies, there are companies that by tradition they have already ion engines like Boeing, and Boeing they make a lot of money with the militaries, so they have very good spacecrafts and they use ion engine. Then you have other ones like Loral that they have been using Hall effect thruster for a long time and they're using Hall effect thruster. So we had also yesterday the operators, and we heard from the operators, Eutelsat, SES, Hispasat was not like that, Eutelsat and SES, they were in this line. For them, what is important is that the business case is good. So if they make money, they don't care. And making money sometimes is not only about the capabilities of the thruster, but it's the whole business plan. So for how long are you going to be thrusting without getting money, all this kind of stuff. So you see there is a place for every technology at this moment. And there is even another technology, is the hemp, which is something between the ion and the Hall, that is not so good maybe as the ion, not so good as the Hall, but they have the capabilities to have an electronics which is very cheap. So you see there is always things coming. So you cannot say this is the best or no. What is true is the Hall effect thruster today is the one which is more expanded and the one that is more sold in the market.
Yes, to complement the question, there is margin in improving the design of the Hall thruster. And what I have commented about the novel design goes in this direction. Okay, we can improve with the material, we can improve with the magnetic topology. And if we understand better what is happening there, we can optimize better the thruster. So I think that for ion thrust it would be also similar. Another point that is interesting, because you have commented about the economics, is the issue of the PPU. At the end, the thruster is the cheapest part of the whole system. The PPU it costs the double of the whole thruster, and I think 3 times the ion thruster, for the PPUs. So at the end of from the market point of view, PPUs, improvements in PPU prices, okay, is going to be also critical.
This is why we said about this German thruster, the hemp, that maybe it's not so good as the other ones from the performance point of view, but the electronics can be half price. And then, of course, this is putting into business. Okay, so there is, another question. Good, questions are coming.
I have actually 2 questions. One is, why is it, because the topologies of the Hall thrusters you showed there is, if I dare say, SPT based with an insulated chamber. Is there any apparent disadvantage of the metallic chamber, the thruster with an anode layer? Mm-hmm. And the second is, I've read some papers about topology for the small scale below 100, below 50 watts, the so-called cylindrical Hall thrusters. And is there any activities in ESA in that direction?
In ESA, at this moment we are looking at this, but still we don't have money for everything, of course. Not because we don't think it's interesting, but it's also a question of funding. We have to concentrate in the technologies that are more interesting. For example, ARC-jets, we took a strategic decision in ESA not to put so much money in ARC-jets because the Americans were so good. When Iridium came, they could make ARC-jets like washing machines. I was there in Seattle, and they have a line, they could sell it, like washing machines. So why to try to compete with something which is impossible? However, Hall effect thrusters and ion engines, we are good. And this is why ESA decided to put the money there. So this is something we have investigations, but at this moment, for us, the important one is Hall effect thrusters, ion engine, and this hemp thing. This is why we are focusing the money there also for European Union.
Yes, there are activities. When I commented about the novel Hall thruster, I say there are other solutions. And one of them is the cylindrical thruster. The cylindrical thruster was an invention of Princeton University, and now there is mainly activity in Japan. Japan is developing, but it's at the level of a research institute and university, where they're working about the cylindrical thruster, where they try to solve some of the problems that you have when you go to low power and you lose efficiency. Then what they get is they take away the central pole, so they have a magnetic configuration that in principle is not so good, but at the same time you have less engineering problems in terms of thermal problems and magnetic problems. Okay, so this is one of the solutions we have. Then you have also commented about the TAL thrusters, that is a Hall thruster with metallic walls. Then there you have a lower control of the electric field that you have inside the chamber. That is also why the chamber then is shorter. In that case, I mean, there is not much in the open literature, or at least I have not followed much the open literature of this type of thruster. It's the one that is implementing this small MIT thruster. This was of this type with metallic walls. Has the advantage that you have the problem of erosion, of sputtering of the wall is much less severe in this type of thruster. So you have lower power losses, that is good, but at the same time, your ionization is not so efficient. So what you gain from one side, you lose from the other. And the two are Russian-based thruster, okay? The SPT and this metallic wall thruster. They have more or less the same efficiency. But for some reasons that I don't know if are industrial company reasons, the TAL has not evolved as far as the SPT. Okay.
Thank you.
Okay, so the last question is there.
I have a question about the simulation problem, and it is which methodology is mainly used nowadays to face it? Maybe statistical or continuum medium like CFD? And which are the principal problems between the results of the simulation and the experiments?
Okay, how much time do I have?
Do it in 3 minutes.
You can have, CFD does not work because this is not a collisional fluid, okay? So classical fluid equation do not work, we have to add equation. MHD, that is close to CFD, usually is not used for Hall thruster. So you have what is called multi-fluid approach. You treat electrons on go as if fluid, ions on another, neutrons on another, and then you have some interaction between these fluids. This usually you cannot get much detail. It's difficult to have a full model of that, okay? There are 1D, quasi-1D, but you don't have 2D models of that. Well, no, there is one. Now, there is one 2D fluid model that is working on Hall thruster, okay? On the other side, you can try to solve what is called the kinetic equation for distribution function. This is crazy because you have too many degrees of freedom, so this does not work. Then close to that, you have what is called the peak formulation, particle in cell. That is the one they have shown in the last slide, this particle, okay? This is the more efficient way to treat this rarefied plasma. The issue is that you have the ion particles, the electron particles. As the difference of mass is so large, when you use what is called a full peak formulation, it takes you weeks or months to get a solution, okay? Because of this difference of masses of the electron ions. So the most successful nowadays codes for Hall thruster are of the hybrid type. You work with ions as particles and electron as a fluid, okay? This gives you a lot of detail. It has some constraint. I'm not going to discuss of them. It has important constraint, but is nowadays the best trade-off among the different numerical methods to deal with that. In the future, with greater parallelization, greater computers, perhaps the full peak will be the solution. Okay.
Thank you very much, Mr. Speaker.